Hi, in this video we're going to talk about sampling. Sampling is the way in which we collect data from a continuous signal and store it as a discrete set of values. Remember that last video I said that our image is discrete? In the same way that other physical phenomena, light is continuous. When we take a picture, we actually take in points of light that will be converted into discrete values that we call pixels. If we capture more points, then our image will have a better detail. This sounds more like a topic for image formation, but it also has an importance when we want to modify images. And to understand it better, we will use the frequency domain that we reviewed on our previous video. Now, for many applications, we might want to reduce the size of an image. Imagine that you want to reduce an image in half. How do you do this? One way could be starting by taking the first pixel and then take every other pixel in both dimensions, skipping one. This subsampling of the image is creating a new grid over the original. Each point will be the pixel values of the new image, but this is not that simple. Imagine that we want to reduce the image 6 times, and using the same procedure, we have a grid like this. The resulted image will be completely white, because the sampling rate was not adequate. This problem is really common in many different areas of signal processing, and the solution was described first by Nyquist. The Nyquist theorem says that if we want to sample a frequency W, the minimum sample frequency should be 2 times W. Let's see this with a one-dimensional example. Imagine that we want to sample this signal. The frequency of this signal is 50 Hz. When we sample any signal, we will always have some information lost, because sampling is a compression procedure. For example, we can take samples of the signal and then we can store those values instead of the whole signal. Then, if we want to recover the original signal, we can take those points and reconstruct the signal. The problem comes when we take less samples. Let's say that we take a sample here, here, and there. When we try to reconstruct this signal, we will end up with something like this. If we reduce the sample frequency more, let's say to 50 Hz, that is the same frequency of the signal, we will end up with a flat line. This is what happened in our checkerboard example. This phenomenon is called aliasing, because when we try to reconstruct an undersampled signal, what we will get is a low frequency replication or an alias of the original signal. Let's see this in the frequency domain. If we get the Fourier transform of this signal, we will have one peak of 50 Hz. According to the Nyquist theorem, the minimal sampling frequency should be twice the frequency of the signal, in this case 100 Hz. But we were actually sampling way under that value. The result is an alias of lower frequency. On images, the result of this aliasing are visual artifacts, like lines appearing where they shouldn't be or missing patterns, just like in our example of the checkerboard. One common way to minimize this effect is by smoothing the image before sampling. The smoothing will remove the high frequencies of the image, avoiding the aliasing due to the new sampling rate. Okay, in this video we talk about sampling. We review the Nyquist theorem and how subsampling can result in aliasing of the image. See you next week!